Right, like that might represent a wave, and you can measure something called a wavelength, and as y'all said, it's like the distance between here and here, the distance between the two tops. It could likewise be defined as the distance between the two troughs, but it's just the distance between two identical points on a wave. And there's also a frequency that can be measured with wavelengths as well. And keep in mind the wave it's moving in space, it's constantly moving. And the frequency would be a measure of, like if this thing were moving and we defined this as our measuring point, how many wavelengths pass that point per second? Okay, so all waves would move at the same speed in a vacuum, and that's called the speed of light in a vacuum. Of course, we're not in a vacuum here because we have molecules in our air, but there is a speed of light in a vacuum. So all waves are moving, and depending on the size of the wavelength, the wave on the top, that's a long wavelength compared to the wave on the bottom. See, that's a shorter wavelength. So if both of these are moving at the same speed, that one on the bottom is going to have a higher frequency, right? Because more of this can pass this point per second or per minute or per hour than this, because it's going to take longer for that bigger one to get through. A good analogy of this in my mind is when you're fishing and the cork's on the water, and the cork, if it bobs really slow, it produces ripples like this top one that are really far apart. Well, if you could count those bobs, that's your frequency. Okay, but then when that cork starts to bob really fast, okay, that's a higher frequency, it produces waves like on the bottom. It produces ripples that are closer together. So you can see that frequency and wavelength are inversely related to each other. In other words, longer wavelength, top, has a shorter frequency. And then shorter wavelengths, bottom, have a higher frequency because more of these pass this point. Okay, so understanding that relationship a little bit. Now, in this chapter, scientists were trying to explain a lot of things that they had seen about light and observed about light. Some of those y'all are aware of. Different colors of light means different amount of heat, doesn't it? I mean, y'all have all seen hot objects glow a certain color. And whether they're red or orange or yellow or blue, doesn't that mean that those are glowing the different colors of light? That's a different temperature, right? The white stuff is typically hotter than red. I mean, red's hot, right? But we know white would be hotter. Scientists were trying to explain that. And they were trying to relate the colors to the energy, right? Heat is energy. The problem was scientists were using classical physics to try to explain it. Well, what's classical physics? Classical physics applies to a ball rolling down a hill, right? A linebacker hitting the quarterback. Large objects colliding, their mass, their velocity, etc. Why did classical physics not fit for what they were doing? Well, because the light that is a result of hot objects glowing, etc., it's from electrons moving. Now, electrons are matter, yes? But they're really, really small pieces of matter. They're some of the smallest pieces that we know of. So electrons are really small bits of matter. Therefore, the laws of classical physics didn't fit. So how come we're talking about waves? If electrons are matter, how come we've got to talk about waves? Well, here's why. There's an experiment, and we're going to watch a video about it in just a second. It's called the double slit experiment. Maybe I should have started the new slide. So what does the double slit experiment do? In the double slit experiment, consider this. If you have a wall and there's a hole in that wall, and if you stand over here and you throw, the video talks about marbles, but let's imagine we're going to throw baseballs at that wall that has a small opening in it. And we're going to look at, on this other side, we're going to look at where those balls hit the wall on the other side. Well, would you agree that the balls should constantly hit right here? Right? Because if they go through that slit, they're going to hit the wall. So, they can't hit it over here. Okay? Because we're going to be standing right here when we throw them. So they're going to go straight through and hit the wall at the back. Okay? So what's so remarkable about that? If you look at water and you put a ripple in water right here, well, water, y'all know, would make ripples like so. And then those waves would start to go through that slit. And then there would be ripples coming out from that slit as well. If we looked at where those water waves hit the wall, then what we would see, guys, is this. If we could measure where the highest intensity hit the wall, we would see a pattern like so. That is called an interference pattern. And there is a diagram of an interference pattern in your book on page 214.
So is that like the places that waves hit?
Where the two crests come together, they result in the strongest spot on the wall. Okay, but where a crest and a trough come together, etc., they cancel out. I think I've got that right. Well, I'll watch the video in a second and make sure. Okay, so that's what happens with waves. So we looked at what happens with baseballs. We looked at what happens with waves, and both of those are matter that we can understand, right? They're macroscopic, big things. So what scientists did, and what the video is going to show you, is they looked at, let's do the same experiment with electrons. Let's stand here and let's shoot electrons at this wall that has a slit in it. When they shot electrons, when they stand here and they shot electrons at this wall, they found that they went through right here. Just like the baseballs or the marbles, right? So electrons are behaving like matter. So then what they did, it's called the double slit experiment, right? So they shot electrons at a wall that had a double slit. Now, where should we see the electrons going through? If electrons are matter, shouldn't they go through there and there, right? Just like a baseball. If you were to throw baseballs at this wall, you would see two exposures on the other side. But what they found when they shot electrons through is an interference pattern. Now, I just realized when I was explaining the water one and the waves and the interference, I should have done a double slit in this wall then too. I just realized that. I'm 8 minutes into my recording and okay. Y'all just watch the whole thing so you're sure to catch that mistake, okay? Anyway, so when they shot electrons through, they got an interference pattern. So what? What does that mean? Well, electrons are matter because they have mass and they take up space. But yet when they get this interference pattern, the electrons are behaving like waves because they're behaving like the water would. And so what this resulted in, y'all, is a whole new area of chemistry/physics called quantum mechanics. So this theoretical physics would not explain what's going on with electrons. We need a new area. We need new formulas. We need new ideas to help explain what's happening with electrons.